Quantitative finance is a world with distinct problems for ML practitioners and data scientists. The sort of data you'll work with has different properties, and the sorts of mental traps and problems you'll encounter also look pretty different. My guest today, Ben Wellington, has extensive experience with these problems. As deputy head of feature forecasting at 2 Sigma, he's seen how NLP and feature forecasting factor into quantitative investing and trading. In addition to how ML looks in quantitative finance, we spoke about how data science can influence local government policy. Ben's I Quant NY project has had a pretty major influence on New York City, motivating changes in areas such as the city's street infrastructure. I think you'll find his perspectives about using simple methods and telling stories through data valuable and refreshing. This is the Gradient Podcast. I'm Daniel Bashir. Here's where I tell you to do all the things about subscribing and following us in all the various places that you're able to follow us. Instead of filling this time with sponsorship ads, I'll just ask you again and again to leave me a rating, to share this with your friends, and anything else you'd like to do. It helps me a lot. Thanks. And now, without further ado, Ben Wellington. Ben, this is, I think, the part of the interview where I rehearse to you things that you already know about yourself, and you kind of like nod knowingly and tell me a little bit more about them. So
okay.
You are doing, I guess, a lot of things right now. You work at 2 Sigma, you're deputy head of feature forecasting. You spend some time at the Pratt Institute as a visiting assistant professor. You have run the data science blog I Quant NY. There's a lot going on for you, and I kind of want to start at the beginning. Like, how does your life evolve? What does that look like for you to walk a path that gets you into doing all of these various things?
Oh yeah, I mean each one was its own mini story. So we can start early on. As I was looking for what I wanted to do, I went to Bucknell for undergrad and was trying to decide what to do next. And I read the websites for different interesting research areas, and I found both Columbia and New York University had these natural language processing programs, which just sounded really, really interesting to me. And I applied, ended up going to NYU, and that got me into the world of natural language processing. And if there's ever like a right place, right time, kind of, this was 2002, so before NLP was cool. But so as that world grew, I was along for the ride, and that was really, really exciting. So that got me into the natural language processing, machine learning space. From there, as I was finishing my graduate program, I remember I did a summer at IBM Research Labs at Watson, and was deciding what I wanted to do next after grad school. And there was obviously there's always this tug between academia and industry and what your advisor wants for you and what you want, and it's this kind of soul searching. It was an interesting time because DARPA was funding a large portion of research in the natural language processing community. So specifically looking into Arabic translation. Again, this is the mid 2000s. So it felt like everywhere I went, everyone was kind of all working towards this one place, and it wasn't super diverse, and it didn't feel really like there was so much dispersion in the things that the leading labs were doing. And when I went and spoke to 2 Sigma, I did an interview there, and it was just really interesting problems, interesting people. Really, it was a small company back then, maybe 150 people-ish. And I had never thought about finance even a little bit, but when I met this group of people, I was just really excited about the diverse problems, the data sets, and ended up joining 2 Sigma, where I've been since then. So this is my first full-time job out of school. We're talking 17 years or so later. So here I am.
It seems like, and we'll get into 2 Sigma pretty soon, but NLP is something that's going to come up, I think, in a few different ways in this interview with 2 Sigma and that discussion as well. But when you described your initial motivations, when you were like thinking of what would be interesting problems for me to work on, what was it about NLP specifically that attracted you then?
I think the intersectionality of of statistics into other spaces was was kind of neat. I was a math and computer science double major, and was always fascinated with the possibilities of combining math and things. And as I saw that interesting combination, I think it just drew me in as a really fascinating way to utilize math. People don't think about when you went to the linguistics professor, they weren't sitting talking about statistics, right? And yet there is this emerging field of computational linguistics. Well, emerging is it had been around for a while, where that was all they thought about. And so you had these two worlds at these schools where people didn't even necessarily talk to each other, but they were trying to solve some of the same questions, one empirically and one maybe more theoretically. And I always found that really interesting.
You did some really interesting work during your PhD, and we don't have to get way too much in detail, but I'm thinking about just a couple of the papers that sort of manifest what you're talking about here. The first one being translational equivalence, which I think did this really interesting thing. Your findings kind of looked at how syntactic constraints, something that one might ordinarily think about putting in a model for language processing, they didn't really help statistical translation models at the time. And right now, we're in a space where I think that we kind of have a single hammer in NLP, and it's getting used everywhere, including translation. So
Absolutely.
when you were working on all this, you started in 2002. I think you finished your PhD in 2007, if I have that right.
Yep.
That's
Yep.
like a very different time. Like, what were kind of the dominant techniques at that time? What were you looking at?
It was a lot of fascinating changes happening then. So, there's always this tug in the computational linguistic field between those that said, we need to use human knowledge of language. We need to understand what nouns and verbs are and subjects, and we need to apply all this parsing to language to understand, in order to, if we're going to ever do anything with language, we need to understand it, and we need to know that this is a color and this is an animal, and that was the view at the time. And so much so that in the 90s, out of UPenn, they built this thing called the Penn Tree Bank. The Penn Tree Bank was a group of grad students employed to sit and tag millions of words of sentences to give training data to these algorithms, right? So if you needed to learn what a noun was, somebody had to go and record the noun in every sentence. So I mean, this took 5-6 years to build out this first version of the Penn Tree Bank, and it became the foundation for modern back then, modern NLP at the time, where it was the data set. Like, where do you get millions of tokens tagged with parts of speech, with sentence structure? You couldn't. It didn't exist. So this was the foundation of a lot of techniques back then. And as we started to explore machine learning, which I was doing, that was what you had to train off of. And at the time, I think I was partially convinced, hey, yeah, you do need to understand the syntax of a sentence to make use out of it. That's kind of how I felt. And so these parsers were going to be useful in order to translate from English to French. It would be nice to know that these two words are a noun phrase, and then we're going to go to the noun phrase in French, and then we're going to invert the order of the adjective because it's French. We can do an inversion, right? So all these thoughts are going through my head. At the same time, enters Google into one of these academic competitions. So there were these hosted competitions every year where who could make the best translator, and these universities are fighting to win these competitions. And one day Google shows up, and they use technology that didn't do any parsing. It didn't do the fancy stuff. It was just a giant word model. It was huge, the biggest model anyone had ever seen, right? Like, and they won this competition, and it just blew the academics away at the time. Like, you're telling me that they came and did the simplest thing, but they had the biggest data, and they beat us all. And all of our advances could not beat the sheer size of data. This was, I don't remember what year the competition was, but it was around the time I was in grad school. And it was kind of foreshadowing the future, if you think about it, right? If you look at what the modern world of LLMs are, they don't need tagged trained data. They don't care what a noun is. They just want to sound human. And if you take this idea that if you have enough data and you push it far enough that you can learn enough things without any human knowledge specifically tagged on it, that's kind of the world that's really burst into the open in the last couple of years, especially in the last year with ChatGPT. And I think those were kind of the early realizations while I was in school of that. So I really call that world, the classic NLP syntactic statistical world, which at this point, it's hard to argue that that is the preeminent movement. but there are those that believe eventually we need to kind of merge the modern ChatGPT, totally data driven, with some sort of knowledge graphy human understanding to have ultimate, AI. But at the moment, I would say that's all kind of back channeled and back on the back burner.
That realization you're talking about, and it seems like this has come in many different ways for a lot of researchers about how they had all these exciting ideas and this extra knowledge and maybe specific inductive biases they could put into models that would make them perform well for certain tasks. And it's just a startling realization that you do what feels like the dumbest thing and you make it big enough and it turns out to perform really well. I think Dario Amodei is another person who really saw this in speech processing. And then he kind of that actually really affected the directions that his research and his thinking took. So I'm wondering for you, kind of having seen that on the Penn tree bank during your PhD, how did that, it obviously, as you're saying, affected your thinking at the time, but I'm kind of curious to what extent that realization kind of manifested in the work that you do now and kind of how you think about tackling problems generally.
Yeah, I think, I mean, I would be lying to say that I foresaw what was going to happen now, right? I'm not going to pretend I did. Um, I do think that even the people working at the forefront of these fields are themselves surprised by their own creation, and how human like one can sound without any human knowledge by just imitating language. Like it's people complain about hallucination and these people, but like these are literally just imitating humans. They don't even know what a dog is, right? It just knows how to speak about a dog. I think I was certainly surprised, but the use of large sets of data is turning back to my work at Two Sigma is where I started at Two Sigma. We've always collected massive amounts of data. In the case of a place at Two Sigma, it's in a financial sciences company. Our goal is to collect as much data as we can about the world and use technology and data science to solve really difficult problems in the financial services industry. And specifically, my world was about predicting the future price movements of different things we trade. It could be like a stock price or something. And in doing that, yeah, we've always had to employ large amounts of diverse data to get somewhere. So I think this idea that large amounts of data is important has always been central. I think the shock is how far you can push it to be human-like. I think that's, like everyone knows we need a lot of data for complex models, fine. Like that's been understood a long time. But the shock is, wow, they really sound like humans. I think that's the disruption that's really taken a lot of people by storm.
That's very true. Yeah. I think that nobody, as you're saying, I feel like nobody can really claim that they weren't surprised in some way about the advances we're seeing. But let's get a little bit on to Two Sigma since you've just introduced that for us. And what I want to talk about, I think, to begin with here is maybe some of the specificities of using data science, machine learning techniques in an area like financial forecasting. I think that when I hear people sort of speaking about this and thinking about the application of these techniques, there's maybe a good amount of skepticism about the possibility of doing this at all because there's just a lot of stochastic behavior in markets. People are annoying in ways that are unpredictable. And so, as somebody who is trying to solve some of these pretty difficult problems, what does it look like for you to apply these techniques? What's helpful about them? What's difficult?
Yeah. So as mentioned in your intro, I'm the deputy head of what's called feature forecasting at Two Sigma. Our goal is to really create novel and interesting features about that might be relevant to our work. And what is a feature? I mean, we could spend days arguing about that, but we see a feature as a piece of information that has some relevance or novelty or usefulness that we can then use. And if you take something like your purest NLP, you're doing machine translation, I guess your features are your corpus, your corpora of data you're training on, and your features might be tokens or words or whatever it is that you're using in your model. Those are kind of features. When it comes to doing things like predicting markets, you need to add a layer well, it's useful to add a layer of human knowledge into the loop to think about what might be important in a data set because the data sets are so diverse and complex. So let me give you an example. And to be clear, the examples I'm giving you aren't necessarily things that we're literally doing, but they're meant to be illustrative. So just to be clear, um, let's say there's been a lot of papers exploring earnings conference calls, right? Every quarter, companies put on, they have these calls and they invite, there's investors and there's questions and there's analysts. And there's, the question is, can you learn anything about a company in that conference call that the market might not yet have fully priced in? So can an algorithm learn something about a company from a call that those trading the stock might not be able to? And so at first blush, you might say, well, the market's very efficient, so the answer might be no. And what we do in feature forecasting is we break that problem down and say, okay, well, what are interesting features about a call that might actually be predictive? I'll give you an example. The number of people who showed up to listen to the call, the number of analysts, right? The number of questions that were asked, the length of those questions, the tone of those questions, the defensiveness of the response to the questions, the number of pauses the CEO made during the speech, the number of, did they use the word I or we when they were speaking? I could go on and on and on. These are sort of hypothesis-driven questions you can ask about a data set, and each of those questions can be made into features where we measure the question. And then once you have these features, you get this really, really rich data set of conference calls where it's not just a bunch of calls, but rather a bunch of characteristics, ideas, hypothesis-driven approaches to these calls. And from there, you can start to feed those to algorithms and or do some sort of even simple linear analysis to say, hey, does the number of the CEOs say predictive of future performance of a company? If they usually say a little bit, and suddenly they're using they're pausing 10 times more than the last 20 calls, like that could be a red flag, right? Can we go back over the last 30 years of calls or 20 years of calls and tease out whether that is a future predictor over those 20 years of a company that might underperform? And if so, we could try to take that idea, build a feature out of it, eventually lead that feature into some sort of prediction. We take these types of small, tiny observations and you put thousands of them or tens of thousands of them or hundreds of thousands of them together, and eventually you get a portfolio of views that has to be stitched together. And that's kind of the underlying of how one can apply a data science to, one way to apply data science to financial markets.
One thing I'm seeing in some of the ways you're articulating these features is thinking about them with respect to baselines and kind of time dependence here. Because in the example of thinking about the number of a CEO says during an answer, for instance, as you kind of brought out, that's not something that is meaningful in a vacuum, but is when you measure it against what is this CEO's normal style of speaking. Maybe they're just somebody who says 20 times between each word. So yeah, I'm kind of curious how you think about like these details as you are working on a problem like this.
Yeah, so in the case of I guess we're gonna put our human ingenuity hat and say, okay, it probably is more important that that's changed than the number of times I said it, right? And so knowing that maybe will lead me to construct that feature in a way that allows me to narrow down my feature set to more relevant ones, right? There might be others where it's less obvious. The tone is it feel like it's positive or negative tone? Obviously, the change in tone is interesting, but you could also argue the tone itself might be interesting too, right? That's a less obvious one. Do I need to do some sort of normalization over time? I don't know. So you might think about that on a hypothesis by hypothesis basis and tune accordingly. Obviously, the other approach is you make every feature, every combination, you do changes, you do deltas, you do percent changes, you could z-score, you put it all in, and you end up with millions and millions of features, and you throw it in some algorithm. The disadvantage of that is that we do believe that humans add value in layering on their knowledge about how the world works, and there's an infinite number of features one could create. And feeding an algorithm an infinite number of features could be overwhelming. So we like the fact that humans can apply some sort of prior knowledge in our feature creation, and that's pretty important.
Yeah, that's really helpful. I also want to talk a little bit about the idea of interpretability and sort of black boxes when you're using computers and computational modeling and investing. And I'm wondering, it seems important that some of the methods you use so that you can do things like debugging and kind of understanding some of these details that you're talking about and refine feature methods, that you should be able to map how an algorithm is responding to certain inputs or certain features that might be important. But again, there is that classic sort of deep learning interpretability performance trade off. And I'm wondering how that kind of pans out for you when you're solving the sorts of problems you deal with.
Yeah, it's a great question. Look, all else being equal, everyone wants interpretability. You give me two models, they're equal performance. One is interpretable, one is not. I'll take the interpretable one every day of the week. The problem is that as these problems get more complex and we start bringing in, things like deep learning, that the interpretability becomes more challenging. And we have to ask ourselves hard questions. What is the trade-off between how much I understand something and performance? And generally, what's important about a black box? I mean, first of all, you want to do your best to understand it, meaning given a set of inputs, can you understand its outputs? Um, People tend to shy away, be nervous about black boxes, but I like to point out that if anyone's ever gone in for surgery, they've gotten general anesthetic. It's actually, this is weird about a lot of medicine. I don't know if a lot of people realize this, but it's a black box. What does that mean? A lot of medicine that we take, a lot of medical things, we actually don't understand. We literally don't know why they work. There's theories, but general anesthetic was applied because there was a scene response. We tested the outputs. We tested them on enough people. We felt comfortable with it. And even though we don't fully understand the mechanism happening, and maybe we maybe in the last few years we made some progress, but in general it's been around a lot longer than we've understood it. And yet here we are as a society comfortable using it because it's important, it's got large gains, we've measured it enough times, and even though we don't understand it, we're going to be willing to move ahead with it. Let's turn our head to a financial model. I would argue we have the same issues, right? We're not going to use it without any understanding of what happens. We're going to run tests. We're going to work to see, okay, well, what happens when we perturb the inputs? What happens to the outputs? And eventually we're going to get comfortable with it enough that we can use it. And when I say use it, I don't mean use it, walk away and ignore it and let it do whatever it wants. I mean, use it, monitor it, have risk, be aware of what's happening, looking for any weird behavior, monitoring weird behavior, flagging weird behavior. If you know your input is suddenly changed, maybe altering or taking down that model, et cetera. So not, even a black box isn't deployed within another black box, right? It's deployed with a lot of cushioning and a lot of observation so that we can keep an eye on things, even if we don't fully understand the reason behind every single trading decision or every single recommendation that might come out of a model.
Yeah, I think this is a really important point. And the medicine example you made is a really good one. I've seen very similar points about the uses of AI in medicine, where in a similar decision calculus, if you are absolutely certain that your model is going to produce the kinds of outputs you want and would be better than not using the model, then there aren't a lot of great justifications. There might be some, but not a lot of great ones to not use it, for instance. And sometimes you might want more detail, but again, you can't always have these things.
Yeah, and I think that's like a reason. I think that's a reason why the adoption of models within medicine is going to be relatively slow, right? Because the ability is going to weigh out our ability. Like the predictivity is going to be way ahead of what a person might fully understand or what can be explained. And so it's great that you're coming and saying, hey, this person has this, issue with their X-ray, but if you can't point to it and say, here's why or what's happening, it raises a lot of questions. And if your answer is, well, the computer said so, but the doctor doesn't understand why, like that's not a good setup, right? So I think there's a lot of research that's just into interpretability, right? People who spend, what they focus on is how to make these things more interpretable. And I think that's going to be growingly important if we're going to be deploying models to more spaces in our life.
Agreed. Yeah. We've been talking pretty broadly about sort of using computers and data science methods in investment problems. And before we dive into, I think, a couple of topics related to uses of AI in investing specifically, I do want to ask a bit about how Two Sigma kind of positions itself within the AI research community and what that research culture kind of looks like.
Yeah, it's a good question. So first, let me say when we started, when I started the company, we were pretty shy. I mean, I would go to conferences and kind of lurk in the back, and people weren't talking about quote data science. That wasn't a term used back then, and we've seen the vocabulary change over time, and we've seen the terms but like fundamentally, we've been doing this for all along, just at larger and larger scale, like a lot of other people. Um, from a cultural point of view today, we see ourselves as we're a firm that first we have to balance the short term with the long term, like a lot of organizations. So we both want to produce predictive models and ship them and do that, in short order because that's where what our goals are to help our investors. But also we want to think long term about what's going to be helping us 5 years from now. And so we need to kind of split our time to the long-term research efforts, which are more, might work out, might not, and the more localized efforts where we have higher priors and get things out quickly. So that's part of kind of the research culture. We also work with universities. We've built partnerships. We have something called the Academic Partnerships Program, where we worked with different professors. We bring some actually work with us in-house. They come and advise for us, or we work with their students. And we also try to publish when we can, not as extensively as a Google who's publishing constantly at all the large at the large conferences, but more on blogs and seminars and in different ways. So that's we do interact with the community in a lot of ways, but but how that has changed over time, and our interactions have grown over time, and they continue to grow, I would say. And I'll also point out that, look, the open source world is hugely important for our work, and we support them in a lot of ways by both giving back code, but also through funding and other ways, because ultimately, if you build something in a container and the world keeps evolving faster and faster, it's very hard to keep up. So you want to really make sure that your tools are wrapped around the open source world, so that as things evolve, as they change, you're getting all those gains along with your own gains in house.
I want to get a little bit more detail from you on the broad strokes of that trade off between short and long term research initiatives and kind of how that manifests for a financial company. Because I think this is just a really kind of canonical problem that every researcher, whether they're in industry or academia, deals with in some way or another. So I'd love to hear a little bit more about what that looks like for you.
Yeah, so we really believe in long-term thinking, and so that's kind of key for us. And it actually kind of differentiates to Sigma from some other spaces, because ultimately, in a lot of investment firms, your value is pretty clearly measured. If your goal is to make a bunch of predictors on different things that someone trades, and then you're correct a lot, I guess that's you're adding a lot of value. If you're incorrect a lot, and that ends up in losing money for a firm, that's not great, right? So one thing you could do is say, hey, go do what you want, but we're gonna, you have to somehow create trades that are predictive. And if you over-index on that, it creates this kind of culture of I gotta get stuff out now. And let me tie this back to the DARPA conversation we had earlier. I also remember when I was in my PhD program in DARPA, well, not only did all these people have DARPA funding, but they were told that you need to make your translation 1% better by January 1st of the next year, or you lose your funding. Now imagine if you're living in an academic world where you have some, I don't know, some accuracy or some F score of 88%, and your goal is to get it to 89%, or you lose all your money. How are you going to think about approaching the problem? Are you going to think big? Are you going to try the next big thing, or are you going to think iteratively because you have a lot at stake? You're going to think iteratively, I think. And what I saw is, as more money poured into these fields, it actually, in some weird ways, squashed innovation, in my opinion, because I saw more and more people fighting for these incremental gains. So I don't think that's great for innovation. And let me bring it back now to my comments on Two Sigma. If you build a world where these goals are set and they're done on a short time scale with incremental gains, you end up with small innovations. And so one of the things Two Sigma does really well is we think longer term. We don't reward people based on just, hey, what happened in the last 6 months, but rather about the work they're doing, about what they're building towards. And we've really built an environment and culture where that long-term thinking is weighted pretty heavily in our approach to, into the value they see in their work. And it's not just about what happened in some, trade or model that was built that was very, very local. And I think that does set us apart from a lot of our competitors who are really more focused on results at the moment, and then they might miss the sort of longer term, wins. And which is why I think we've been doing things like natural language processing for as long as we have, because it took a lot of years to get right, right? Honestly, I did it a long time, and before things went really well, it was hard. There's a lot of failure. The financial markets are very competitive, and you have to be willing to fail in order to succeed. And if you're not patient at failure, then I mean, ask the Wright brothers, right? I'm sure there's a lot of plane crashes, I'm sure, before they took off. So
Indeed, yeah. It's like you have to be really careful about how you're crafting your incentive structure, right? Because
exactly.
whatever you do with that, people are going to respond to it in really, really important and kind of complicated ways.
Yeah, you're precise. Yeah, you're hitting it right on the head. That's exactly right.
I want to talk a little bit more about more of the details around the uses of AI investing for Two Sigma. And we already talked about a couple of examples and cases of what this might look like. So you talked about looking at different features of conference calls, for instance. But I'd love to know at kind of an even higher level than that, since Two Sigma has been using AI for over a decade. What, like, in the broad strokes in the investment strategy, how these methods kind of fit in and how that's evolved over the time that Two Sigma has been using AI techniques.
Yeah, so this gets into the specifics of the semantics of what is AI, what is machine learning, right? And it's interesting, right? If it, like a linear regression, doesn't feel like AI or machine learning. As you add a regularizer, as you make things more complex, at what point do you say, oh, and maybe as soon as it's nonlinear, that's one answer. It's a fine answer. So it's hard for me to say like that there was some point where we started using. I mean, it's been on the spectrum the whole time. What I can say is that the complexity of that spectrum, obviously, on the most complex side, that the space has grown. Deep learning is inherently more complex than support vector machines were, and so as that field has grown, yeah, we have a higher weight of our work and attention on some of the more complex areas than we did in the past when there was not as much complexity there. So like the percent of our work that you might consider, I don't know, AI at first blush grows over time as the amount of techniques in that space grows. So maybe when I started, it was much more linear in a lot of work. There was more statistics. And again, like what is statistics versus ML? People could fight about that all day. But certainly there was more linear approaches to work. And the nonlinear work has been around a very long time, but the percent has grown to the point where probably the majority of our approaches nowadays would not be just some linear approach where you're mapping some single data point to some predictor. Part of that, by the way, is not just the creation of newer technologies, but also the saturation of people using these approaches, right? If you're the only one with an idea of how to use a piece of data to trade a stock, then you don't need to do anything complex to trade it. It's just kind of staring you in the face, right? But as more and more people are aware of that, suddenly the price will shift very, very quickly. Because if you know something and someone else knows something, then they're going to raise the price to something. And so what we see is as your competition learns things, the ideas that used to work less good over time, and you need to reach farther into maybe more black boxy things or more clever data sets or more clever features to keep that edge on the competition who might be coming and eating up some of the older work that you've done.
So it seems like this, when you're kind of in financial markets, you're competing to make money and you have all these other people, everybody has pretty similar information. A lot of it is sort of this game of, you were talking about the features one might extract earlier. Do you feel like you describe a lot of investing as who can come up with salient features and find things that other people maybe hadn't noticed, that hadn't quite been priced in, and just sort of develop alpha based off of that?
I think that's one of the key components, I guess. So there's who has the best and most deep history and rich data, right? You need the data to make the features. So that's a big thing, right? Because um, uh, if you if you don't have a vast data trove, then you can only do so much. So and there's also the fact that we've recorded our data and the point in timeness, which we can get to in a minute if you want, the importance of time. We can talk about that. But having a rich data set is important. So that's one. Two, yes, absolutely. The goal of feature forecasting is to create, as you said, novel features that are creative, that people probably haven't thought of, based on a bunch of maybe novel data sets or maybe known data sets, but just looked at in creative ways, right? This is where we can even use AI to create features themselves. You know, you think of features going into AI, but AI can go through a earnings conference call voice recording and find interesting things about it that then become features, right? So so the creation of features can also use AI. And then once you have those features, the third leg, you have data, you have your features, and then there's, of course, how do you combine all these features? How do you trade them? You know, what techniques do you use? What type of machine learning or AI are you using there? That's a big part of it as part of the competition. And then even once you have all these predictions, now given all the predictions, what's your portfolio look like? How do you execute? That's all downstream from my work, so it's not my expertise, but it is also a key component of being competitive in markets.
That's helpful. Yeah. I would love to talk a little bit about the importance of time and data that you were speaking about. And I guess this kind of comes up in lots of ways because when we're thinking about that role of time, it seems like there's a lot of trickiness and the sorts of claims you can make when you're doing things like maybe back testing or just testing predictions and hypotheses. So I'd love for you to talk a little bit about the challenges this introduces and then how you think about addressing them.
Yeah, absolutely. This is a huge part of the importance of recording data. The only true point in time data, we call point in time, meaning like we know the exact timestamp this data created and we know the exact form it was in. The only way to know those things is to record. When you buy it from somebody, you don't actually know that the timestamps that they're giving you are the actual timestamps that data would have been available to you. And that's important because if the data wasn't actually in the world, then the market couldn't have responded. So I'll give you some like key examples. One would be a news agency that has a bunch of news stories and they use topic codes and they apply topic codes to their stories. So this story is about interest rates, this story. And one day they say, hey, you know what, we need a new topic code. We'll call it subprime. And the reason they created that topic code is because it became very interesting. All these things happen in the market. So they went back and they wrote some code and they backfilled all their stories with a new topic code called subprime. All right. Now it might get applied to a story in 2006, but it didn't exist in 2006. You know, they didn't think to add it, let's say, till 2008. I don't know. But the story in 2006 suddenly has a topic code that only exists because someone in 2008 thought it was a good idea. In comes your backtest. La 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 la. Here's a story, 2006. Look at this topic code. You feed it to a machine learning algorithm. The machine learning algorithm suddenly says, "Wow, you know, this seems like a bad thing. Let's short the." And you convince yourself that I could have made all this money if I passed this topic code into my machine learning algorithm. It would have made all this money. But it's actually a backwards argument, right? The only reason it's in there is because it would have made money. And so if you had actually been recording the news, you would have seen that story didn't have that topic code in 2006. And that's really, really key. And so much so that we've had like a large news organization come to Two Sigma and ask for the recording of their own data to repurchase it back. In other words, they hadn't been recording their own wire. They only had their edited version. And so they said, hey, I know you have a version of our data. Can we buy it back from you? So that's kind of the kind of way we think of this point in time data. And I'll give you like a much more serious example. There's a lot of people doing these days news analytics where they say, oh, I've got Twitter sentiment and I've got all these things and I'm recording all this stuff. And they might come to me and say, look, I've got this product and it's the Twitter sentiment on the S&P 500. And I think it's predictive. If you track what people are saying on Twitter about the S&P 500 companies, you can make a trading strategy then. I'll say, okay. So you get the data from them. And sure enough, you look at the S&P 500, it's got all 500 stocks, and then it's got the history of all the tweets about them for the last, say, 10 years. What's the problem with that? The problem with that is that it's today's S&P 500 for the last 10 years. But 10 years ago, you didn't know what the S&P 500 was going to be in 10 years. It is true that if you told me 10 years ago, here's the 500 companies that will be in the S&P 500 10 years from now, that we could make money. Like, yes, if you tell me today, the list of S&P 500 companies in the next decade, you can profit off that. So what happened there is that a vendor who didn't think about it created a version of S&P 500 based on today backfilled, as opposed to a version where they give you for every day only the companies that were in that day. And by doing so, they've projected information about the future into the past, handed it to you. You run your algorithm and you say, all I have to do is buy every company and I can be very profitable. Forget the sentiment. I'm just going to buy anyone who tweets, let's buy. So those are the kind of intricacies that and they're not like, it's not that a vendor is being, trying to be deceitful, but rather they don't think about things in the same way about how important a timestamp is to a market. And if you don't get that timestamp right, it blows up your entire, you think you've built the strategy, but then you go and deploy it and it just falls flat because it can't see the future.
So when you finally come up with a strategy that avoids all of these foot guns, one thing that's kind of very often repeated to people who might potentially want to invest is how difficult it is to beat the market. And so for a firm like Two Sigma that is ostensibly wanting to do that and to make money for its investors, how do you think about kind of the abilities of the techniques you use and what they kind of can do when you're avoiding all of these tripwires in order to actually do that?
Yeah, so let me point out a couple challenges that's specific to finance and AI that people don't necessarily think about. We'll start there, and then we can talk about how we can, how we look at it. One specific challenge is the fact that your training data doesn't actually explain the thing you're trying to predict. So what do I mean by that? It only explains a tiny portion of it. So imagine if you are now going to be, and I give you pictures and I say, I'm going to use AI and you tell me this is a cat or a dog. And you look at this picture and there's enough information in this picture to say if it's cat or dog. So you train the computer can figure that out, right? And there's enough information there no matter what. Now, that's not the world that we live in, right? Because there isn't anything that has enough information like that to tell us, will the market go up or down? That doesn't exist. But imagine instead if I gave you 5 pixels of the picture and I said, all right, now tell me if it's a cat or a dog. The problem becomes much harder because you only have a tiny piece of whether that's a cat or a dog or not. And that's what we do in finance, right? The price of a stock price, for example, of a company, it has so many inputs. You mentioned earlier that there's human behavior. There's so many things happening, and I'm sitting here looking at one data set. Maybe I'm looking at weather, and it's only a tiny, tiny, tiny piece of the story of that price. So I don't expect to be able to predict that price particularly well, but I do expect to predict it better than average, better than more than 50% of the time, right? So you end up with an R squared of 0.01, and that's the greatest R squared you've ever had. I mean, being able to predict even the tiniest bit, and the way a financial company can then utilize that is, yeah, you can only predict a tiny piece of it, but you can do it at scale. You can do it for tens of thousands of companies round the clock. And for each one, if you're just right a tiny bit, but you scale that up, you suddenly can actually, you can actually trade a successful portfolio. And so on the one hand, you say it's really hard to predict, a tiny R squared, you're not even being predictive. On the other hand, I say, no, you are being predictive. It's statistically significant. It's real. It's just small. But if you put enough small things together, you get something big. And that's the underlying challenge of financial markets. Yeah.
That's a helpful picture. So it's really more like as you're saying, you're blending a lot of really small wins, and that ultimately is sort of what gets you ahead.
Exactly. And when we talk about these models, some of these models are really just one of those small wins, right? If I make the model where I really trade off the CEO's obviously that's not going to be the giant part of what Two Sigma does, but it might be one tiny, tiny, tiny piece that's a little predictive. And then someone else might do the model on the number of people who showed up for the call, and is that predictive of anything? Does that tell us anything about future, what's going to happen? Or whether the call started late or not. What does that tell us? If it started 5 minutes late, that could be a red flag. So, each of these features could be part of a hypothesis, part of a model, and each one is not meant to tell you everything about a company's price. In fact, they never could. They're just meant to tell you the slightest little hint that's big enough to actually monetize when done at scale.
So, among a lot of the cases that we've been talking about when it comes to uses of AI in investing, the really notable thing that you've brought out in many different ways is the importance of kind of locality and time to them. That when you're developing an investment strategy, you have to be really careful about when things are happening, what is occurring in the market, and one time is not necessarily going to be occurring at a different time. And so it seems hard to take a strategy that would be applicable for something involving maybe a certain set of companies at a given time and kind of transplanting it elsewhere. And what that makes me wonder about is then when it comes to uses of these techniques in finance, how reproducibility looks.
Yeah, it depends. I mean, reproducibility has two meanings to me, and there's the obvious one and the less obvious one. The obvious one is the sort of notion of scientific reproducibility, which is the underpinning of good science, right? We want any experiment that we run to be reproducible in general. We achieve that at a firm like Two Sigma by creating a simulation environment. And ideally, given the same inputs and the same data, your simulator hopefully produces, the same outputs unless you create some sort of non-determinism in there. So we generally hope that our work is reproducible in the general sense of science. When we're building some sort of model, it's based on a hypothesis. We test that hypothesis. We go through in sample and out sample, and once we feel good about that, we have to write an academic style paper at the end, maybe not as rigorous as, of course, as a conference paper. And the hope is that from there, our work is reproducible to someone else. So in that notion, reproducibility at a place like Two Sigma mirrors that of general science. So that's the good news. Where are the things that kind of get a little messy? Number one, let's look at our reliance on outside tools. The classic example is Google Translate. Now, let's pretend that I work with textual data, and let's pretend that I'm using Google Translate in this made-up world to translate Chinese newspaper headlines to then run some natural language processing on them. And I say, hey, Google Translate's great. Let me run it through there, and it's going to tell me all this stuff. And I train some model, and it's great. And then the next day, Google makes an upgrade to Google Translate, and they made it, quote, better. And I put that in quotes because to someone out there, a better translation is a good thing. But at a place like Two Sigma, I don't want a better translation. I just want a non-changing translation. I just want to wake up each day and have the translator unchanged. Because as soon as you change the algorithm that you're using, the reproducibility goes away. There's nothing you can do that's reproducibility. You're injecting a bunch of non-determinism in your process. And that means that if I run a controlled experiment, and then I edit some variable, and then my output changes, do I know that it's my variable I edited, the thing I changed, or could it be the fact that Google just released a new version of Google Translate? So from that sense, reproducibility is challenging for really anyone in the world using using something like ChatGPT or Google Translate, right? Like if the underlying software that you're using is changing under you, then reproducibility in its fullest extent is quite challenging. So that's not just a finance specific thing, but it is one in the real world application.
I guess I was just going to kind of reference that anybody, as you said, messing around with LLMs right now. And I guess an example that I've given to people was the New York Times versus OpenAI lawsuit. There were a lot of tweets about how you could get ChatGPT to basically produce verbatim very long passages from New York Times articles. And I looked at these maybe a couple hours later, tried basically the exact same prompts, and by that time, OpenAI had kind of come in with some duct tape to figure that out.
Right. And somewhere a scientist is crying because they're trying to run an experiment and the underlying material that people are using is changing. And look, in the perfect world, our methods are robust to changes, right? If somebody tweaking that ruined your model of the world, that's probably a red flag of robustness. So I don't think that, I'm not saying that things can't change, but it certainly makes science more difficult when your inputs are science. And how do you fight back? Well, you build your own tooling and you build out your own set of things for which you do have control, right? That's where your reliance on open source can be helpful. By building your own set of tools, your own models, then you control the versioning. You control when it changes, and suddenly you're empowered to reproduce your experiments. And that's really important at a place like 2 Sigma where we want to be very careful that what we're studying is what we think we're studying.
This is some really good advice for, I think, for people doing lots of different things in engineering and across the sciences. And I think I want to kind of jump off from that to move into some of the other work you've done. So, for a while, you've been running this blog called I Quant NY, and you gave a really wonderful TED talk about some of the takeaways you've had in this. And really, at the core of it, is you found a number of interesting, I guess I'll call them phenomena about the city based off of some of the open data that's available about it. And you've been able to tell just really, really good stories about it, many of which have even gotten to the point of going to the city itself and kind of influencing policymakers. And I kind of want to understand how this came about, and then maybe how this work has influenced how you kind of position yourself as somebody who does this sort of work, who does data science and works with these sorts of methods.
Sure. We could start with how it came about. I mean, on the one hand, at work, I'm running more sophisticated algorithms, and sure, we want interpretability, but it doesn't need to be interpretable in the sense that everyone in the world understands it. Rather, a subset of people. When you start opening up things to a larger group, the ability to do complex things starts to decrease, right? If you want to be able to explain what you're doing to, say, a city official somewhere, you probably don't want to get into the nuances of neural networks. So as I started to explore city data, I started to think about how to use it, and this came about in, I want to say, 2012, New York City. But we can edit that out. So this came about in about 2000, I can't remember if it was 12 or 14, I believe, that Mayor Bloomberg passed the open data laws in New York City. And this really made the data that our city collected start to be available to the public so that anyone could get their hands on it. And as I started to look through the data, I was wondering, does anyone actually use this for anything? And sure, I could throw it in a machine learning algorithm and build some crime prediction, but that wasn't going to be like interpretable to anyone. So I took a different approach, which is really using descriptive statistics in its basic form, doing things like counting and finding outliers, and started to analyze data sets around the city. The first one that I did was on a closing hospital. Long Island College Hospital was closing in Brooklyn, and people were debating, who was most affected by this closure. And I built this map that was just mean distance to a hospital before the closure and after the closure. And then I subtracted the two. And so it gave me a map of the city with the delta of a distance to a hospital on every home, which was kind of like a new way to look at this. And I realized that Red Hook, this part of Brooklyn, was kind of the most affected, which wasn't even part of the dialogue at the time. So I wrote about that, and it got covered in some blogs. And I realized that there's this sort of appetite to tap information, and with it you can start to like really move policy and change things. And from there started blogging and watching each of these posts get kind of circulated through different news outlets and things like that, and was having a really good time.
Yeah, and kind of as you mentioned, the sorts of things that we're doing here, more storytelling focused, engagement with the public, civic engagement, and using different sorts of methods from what you do in your day-to-day work. Has that kind of rounded out for you, I suppose, how you see yourself as a, I guess, I don't know what kind of term you would use to describe yourself as a professional, but like somebody who uses data science and forecasting methods and all of this?
Yeah, I think the ability to communicate is one of the core skills needed for even for science, right? Like, you could do climate science, talk about global warming all day, but if you can't explain to people what you're doing, then what is it for, right? You need that communication, and you might wonder whether communication becomes a core part of science curriculum. That might make sense to invest more there. Um, I'll give you some like stories. One was, because it's relatable, about parking tickets, and specifically there were these fire hydrants in New York City, and if you park within 15 feet, a lot of people carry around tape measure when they park, but if you park within 15 feet of a fire hydrant, you get this really expensive ticket. It's over $150. And I realized this data was public, that we could actually map the revenue of every fire hydrant in New York City. And it turned out that there were these two fire hydrants in the Lower East Side of Manhattan that together were making over $55,000 a year just being fire hydrants. And they did that by kind of luring cars into this, what looked like a parking spot, but wasn't, and it was confusing. And so you can imagine getting a parking ticket in the same spot if this kept happening for years and years and years, but who's ever going to stop and fix it, right? And the answer might be nobody. But if you start to look for outliers, which I did in the data, you can start to be like, oh, wow, there are these problems. And you're never going to find that outlier ticket by ticket by ticket. You're only going to get it through aggregating. And so when I did, I wrote about this, and it made it into the the New York Post, and other organizations picked it up off of Reddit, which I used to post things. And eventually, the Department of Transportation responded, we haven't known about this, but we're gonna review it. And 3 or 4 weeks later, I came back to the spot, and they had repainted the parking spot. They had made what's called zebra stripes, which tells people don't park here. And it was kind of like a moment, like making data interpretable changed the streets of New York, in a small way. But imagine if everyone had that kind of data at their fingertips. Imagine if data literacy went up, what the world could be like. Because when you're a person complaining about a parking ticket, you're like everyone else. But if you're a person who can take data, make a narrative out of it, and bring that data to the forefront, you can actually make change. You can convince people. You're not just the complaining person anymore. You're the person that's measuring some impact and getting movement. And that's like a silly example, but there are others that I worked with where the city made various changes, like reprogramming the back of taxi cab tipping algorithms, and retraining police officers, and other things that came about just by outlier hunting.
This is really interesting because when it comes to the sort of statistical view that people tend to take on really large scale phenomena, there's often this, I want to say, something like a criticism that gets made when you reduce a lot of things to just numbers and descriptive statistics. Then it's really hard to engage people the same way you can with things like stories. I think in your case, what I see is, I mean, your blog has this combination of statistics about things that are obviously of interest to your target audience, New Yorkers, because everybody has these experiences they can probably relate to of getting parking tickets. And then you're also doing like a little bit of kind of investigative journalism style stuff. You went and actually saw those curbs. But I'm curious, also in some of these stories, how much personal experience you have with some of these issues that you tend to investigate, like parking tickets, and then how much, if at all, that kind of comes together with the narratives you tell through data.
Yeah, absolutely. I mean, there's two ways to come across a quote story, a blog post, I guess I would call it, right? One is you start with an idea about your observations in life, and you follow that, you pull that thread. Like, I've noticed this is the case, and then you start to look it up, and that's really the hypothesis-driven approach, where you're going and exploring whether your observation, plays itself out. That's the classic scientific approach that probably is the stronger way to go. The other is the data-driven approach, which you have to be more careful of, because it can lead you into overfitting and missing things. But in general, it's, hey, browse things, look for interesting tidbits, and then pull that thread. So I'll give you another example. I once mapped New York City for, I was curious which people from which state got parking tickets in which neighborhood, which is another way to look at like where people were driving, right? So if you were from New Jersey, which is west of New York City, people tended to go through this tunnel and get tickets in Manhattan. But every neighborhood had its own kind of state imprint. My favorite thing that I found in looking at that, which I hadn't thought of until I looked, was basically Williamsburg, which is like one of the hippest, coolest parts of Brooklyn, also was where Californians got their most parking tickets. So if you look at a map of California parking tickets through New York City, you'll see that the coolest neighborhoods have the most California license plate tickets, which is kind of like, a way of measuring coolness of a state. And again, I didn't come in with that idea, but when I saw the map of California parking tickets, my jaw dropped as I mapped it over my view of hipness across states. And those are the kind of things that just pop out that you would never think of in advance. And by the way, I should add that when I wrote about this, I remember a newspaper called and they were interviewing me and said, "Well, how did you do this?" And I was like, "I counted." And they're like, "No, but how?" I'm like, "I counted." And that just gets to the core of what I was really trying to do, which is really just basic things that no one had ever looked at. And going off that, by the way, you do have to be careful. You're exactly right. Like you can't you can overstate just by doing this and not doing a rigorous statistical analysis. You have to be careful in what you're saying. You can't make a giant inference about the world. You can't say, without robust statistics, you have to be very, very careful. And I was very, very careful in general, but I must admit that people can misinterpret your own work and take it too far. For example, I once wrote about restaurant health inspections, and I measured all the fast food in New York City, and it turned out that White Castle had the cleanest health inspection record. And a news agency sent the reporter down to the parking lot, and I'll never forget they were interviewing someone, and they said, "How do you feel about this study?" Which, by the way, was not a study. "How do you feel about this study?" And she said, "I knew White Castle was healthy." And I'm sitting there going, "Oh, what have I done? It's not the narrative I was going for." So even if you're careful, even if you're putting out things and not overstating things, people can take little bits of what you're doing and run with them and misreport how you said it. So that's always a risk in this work.
People really do like reading almost whatever they want into all things, all the way from, I guess, fun exploratory data analyses to like real scientific findings, and not the best thing in the world. But I think there's a really good takeaway from all this too for people who might be listening to this who are researchers, for example, which is just that there is so much to be done. And I think people have probably heard this before, but it's always worth repeating that there's so much to be done, not necessarily in inventing new methods of, say, scientific inquiry, but in taking the basics of what you already know and just doing something with it that nobody's done before, or going and investigating something nobody's done before.
Right. And that's how Two Sigma looks at it as well in my professional work, right? It's not always about the most complex model you can apply to something, right? If you have a good idea, if you have an intuition and you're looking at something that no one's ever looked at before, sometimes just doing something very simple is gonna pop because it's novel, not because of its complexity or that it's the latest AI, but rather it's just creative. And yeah, and I think the other thing to take out of it is as scientists on the communication, which we talked about before. I'll give you one more example of some work I did, which was studying, in New York, we have this what's called combined sewer outflow. So when it rains, all the water goes into the sewer, and if it overflows, it mixes with the sewage, and then it gets released into the waterways, which leads to kind of a gross, situation. But they measure this through these things called fecal coliform, which is a bacteria level. And I was once doing a study, and I wanted to show the place in New York that had the highest amount of fecal coliform in the water, which meant there was the most sewage. These numbers would come back like 5 milligrams per milliliter of water, or 18, and these numbers just meant nothing, right? I could write a report and say, "Did you know that Coney Island Creek has 5 milligrams per milliliter?" And everyone would just stare at me and be like, "That means nothing." And to the scientist who lives and breathes that stuff, that means everything. But to 99.999% of people, that means nothing. So how do we speak as scientists in units that people can understand and take in? And for that one, I thought it was kind of a nice conversion where I converted it from a measurement of milligrams per milliliter to a measurement of the percent of days where it would be illegal to get in the water because it was too dirty above New York state standards. And so suddenly, instead of me saying, "Oh, it's 5 milligrams per milliliter," I'm saying, "Hey, 70% of days measured, the amount of sewage in the water is so high it would be illegal to swim." Like that's going to catch your attention. So how do scientists speak and convert and make sure that they hit you in that spot? I think that's a key to move science forward.
Yeah, it's really a good bridging from just numbers and the kind of communication we traffic in internally in just kind of scientific paradigms to that. What is How does that manifest in the daily experience that people can just relate to, as in your example of, well, I go swimming, so what would it look like for me to not be able to swim because this water is so dirty?
Right, exactly. It's the personalization of the science for people. You could say, look, the Earth is heating up by X degrees. Again, like that's not personal. But hey, there's this hurricane's hitting, blah blah blah. That is personal. So it really that's the same kind of Unix version that we're talking about. And in order to get movement, you really need to speak people's language.
Yeah, I think a good last section for us, and this is also kind of on the storytelling beat, is you talk quite a bit about how you spend time outside of work doing improv comedy, and I think that's like a very different sort of thing from this, but I also see how it fits in very well with this. How do you communicate with people? How do you construct stories? And so I guess I'd love to hear you talk about a little bit about this and how you feel it's kind of impacted you as a storyteller and communicator.
Sure. I mean, the core tenet of improv, if you ever do improv or take a class, there's this idea of yes and. And it's this idea that, let's say there's two people and someone says, hey, I'm a doctor and I'm here to help. And the other person in this scene says, you're not a doctor, you're a shark. I mean, that scene is just going to be terrible because they didn't build off each other. They're just saying no and they're arguing, right? This is kind of when you're doing teamwork or building or doing science, really, we all build off of each other, right? And I like to think of it through the lens of yes-anding each other, right? Like people have ideas and they're all probably good ideas and we build off. So, hey, I'm here, I'm a doctor. And the other person says, thank God the baby's coming in 3 minutes. Like that's a much better answer than no, you're not, you're a shark, right? Because it fundamentally is taking someone's idea and then building it up. So I think that's kind of core for collaboration for in any sort of space to make everyone feel like you're adding to each other. And it's a really core skill I've taken from improv and brought to my professional career and work. The other thing I think is specificity. It's another thing in improv. If you're having a scene and you say, hey, can you pass a cereal? Maybe that's not that interesting. If you say, hey, can you pass the Fruity Pebbles? Like, what is that? You're already saying a lot more about the person. That specificity is important when giving a narrative and not generalizing. And I use that a lot in my storytelling with the city to kind of tie it all back into our lives and to really catch people's attention. So those are some of the parallels that I found.
Yeah, I think that there's, again, kind of a lot in there, the additivity and specificity. I think these are also some really good kind of takeaways for us to end on. So I think with that, Ben, I'll thank you for being so generous with your time and for speaking with me. I've really learned a lot from talking to you, and I think your work is really, really interesting. So thanks for taking the time to talk to me about it.
Yeah, thanks. I love the conversation and excited to speak to you. So thanks for your time.
That's it. That's the whole episode. Thank you for listening. If you like this, really the best thing you can do is to leave me a review and to share this episode with someone who might find it interesting. You can also subscribe to the podcast in your favorite podcast player, and if you want to keep up to date with the latest from The Gradient, to receive emails whenever we have new podcasts, newsletters, articles, then you can subscribe to us on Substack, where you'll get email notifications for everything.